In the next section, we will recycle the PID algorithm for a number of control applications. The control algorithm is modified, but instead of implementing this modified algorithm in an FB, in a function block, we recycle the standard PID algorithm that you can find in the libraries, in the control libraries of the vendors. And we do this because it is ready for use and comes with a nice faceplate. Well, indeed, re-implementing a control algorithm would be very work intensive because the end user of the algorithm is expecting, for instance, manual and automatic modes, internal and external set points, tracking, a nice faceplate, so a nice human-machine interface, set point handling. Of course, he expects also documentation, right, and guarantees of a good implementation, mechanisms for handling wind up and feed forward, alarm handling, and so on. So you can see that it's better to fall back on what is available, for instance, a standard PI controller implemented by the vendor. In this first subsection, we deal with digital MVs. So this means that MV can only take a finite set of predetermined possibilities. In our case here, 2 or 3, depending on the type of actuator. Well, we'll start first with proportional actuators, and they are also known as all or nothing actuators. For instance, a good example is a conveyor belt, and we have considered it before. There are 2 states, right? Either the conveyor belt is running or it is pausing. Or you can have also temperature control. You have 2 states, either you're heating or not. And then finally another example is, for instance, the inverter, right? You have 2 states, either the top transistor is conducting or the bottom transistor is conducting, and depending on which transistor is conducting, the output will either be high or low in voltage. Why is this type of actuator called a proportional actuator? Well, if you take a period of time, t, right? This is this period of time, and you consider a duty cycle, that is the proportion of time where, well, the actuator or the state is on, right? So if you have here a duty cycle of, let us say, 50%, this means that in this period of time, well, 50% of the time, right, you have on, right, and 50% of the time you have off, right? Well, for a proportional actuator, and you take for instance the example of the conveyor belt, well, the output discharge will be directly proportional to the duty cycle, right? Well, if you take temperature control, well, the amount of energy that goes to the system will be proportional to the duty cycle. And for the inverter, well, the output voltage will be directly proportional to the duty cycle. This is where this name proportional actuator is coming from. Well, the next actuator that we'll consider is the integral type actuator. Well, for the previous type of actuator, the proportional actuator, we had 2 states. Here we'll have 3 states, right? And this is why the integral actuator is also known as the 3-point actuator. An example is the electrovalve, right? It's a valve that is driven by a constant speed motor. So the 3 states are open, right? Assuming that the pressure in the line is constant, well, you increase the flow. Close, and this will decrease the flow. And stop, well, this will maintain the valve opening, right? And this will therefore maintain the flow, again assuming that the pressure is constant in the line. And what is done is that this can be implemented using two digital inputs, I should say binary or Boolean inputs, right? Well, this one, first input to 1 opens the valve, so this corresponds to this situation over here. This is open. The second input to 1 corresponds to this one, so this corresponds to close. And well, if both inputs are 0, this corresponds to maintain the valve position, so this is stop. And if you take two binary inputs, you have 4 possibilities, but you have only 3 states, so obviously this one is prohibited to have 2 inputs that are 1. Well, let us summarize this. We have 2 types of actuators, proportional and integral actuators. If we talk about the proportional actuator, well, there are only 2 states, and this is when this third state here is not applicable. If the output of the controller is 0, this means, for instance, if we take the case of a conveyor belt, that the conveyor belt is not running, so there is no output discharge. If the conveyor belt is running, well, there is a given output discharge X, expressed here in kilos per second. Well, if you play with the duty cycle, this is the proportion of time where the conveyor belt is running in a given period. Well, you can have an average discharge in this period of time that lies in between 0 and X. Hence the name proportional actuator. Well, for the integral actuator we have 3 states. So this will be stop, right? This will be open, and this will be close, right? So indeed, if MV is equal to 0, this means that the command that is sent to the electromotor is 0, so the valve opening will be constant, right? Let us say 50%, and you'll have an associated constant output flow, let us say 1000 liters per minute. But now, if at this time instant over here we send the command open, right, since we have a constant speed motor, the valve opening will start to increase linearly, and you'll have a linear increase of the output flow, right? If you send the command close, again here at this time instant, the valve opening will be decreasing linearly, and of course the associated flow will follow, and there will also be a linear decrease of the flow. In practice you might deviate a little bit from the characteristics that you see here on the slide, because in reality you'll have to take into account the valve characteristics, which might be slightly non-linear, and you might have to take into account pressure variations in the line. For proportional type digital actuators, you can use pulse width modulation, or PWM, in French, modulation de la largeur d'impulsion. Well, typically this duty cycle, which is the proportion of the on time to the regular interval, right, T cycle, is set by a controller, and typically it will be a PI controller, right? So the controller output will be the duty cycle, so MV will be the duty cycle, and then you can find the on time by this equation over here, right? Do not use PWM for integral type digital actuators. Anyway, this would be difficult because, the duty cycle, when you translate it to a state, will only produce 2 states, on and off, and as you know, for an integral type digital actuator, you have three states. Pulse width modulation you have encountered in other courses that involve power electronics. Well, this is how you can visualize things. A standard controller, mostly a PI controller, right? So we'll put this D action here between parentheses, is, well, running at a sampling period. TS control, right, is equal to T cycle, and it is producing the duty cycle, right? And this duty cycle is then translated in an on time. So here in this cycle period, right, we have that the output of the controller is 30%. This means that the proportion of the time that, well, the output will be on is 30%, as you can see here visually. As discussed before, for integral type digital actuators, we'll have to come up with another type of algorithm. In process industry, the integral type actuator that is encountered most is the electrovalve. It offers precision, and the advantage is that in the case of failure, well, electrovalves will remain in position, and this can be useful for some applications. Some electrovalves offer two additional binary outputs that tell you if the valve is closed, right, or 100% open, and these binary outputs can be used for control. Well, usually the valve position is available for feedback. If this is not the case, we'll have to find an algorithm that does without, and it is in this case that these two additional binary outputs can be used. For integral type digital actuators, and this is now in general, we want to prevent damage associated with frequent, well, state changes, going from open to close or close to open without going through the stop state. You will find these kind of limitations in mechanical systems to mitigate inertial effects, and in electrical systems to, for instance, limit shortcut currents in transistors. Two parameters are used to constrain the two binary outputs: the minimum pulse time, and the idea is that below a certain value, the pulse open or close will have no effect on the system. The minimum break time is to impose a minimum break or minimum pause when changing direction. So for instance, it is impossible to go from open to close without this minimum break time. Well, the motor time is the time that is needed to go from a fully closed to a fully open actuator, or vice versa. This time is indicative of the dynamics associated to the actuator and is needed when there is no valve position feedback, as we will see next. Let us consider the example of the three-way mixing valve. We have two binary signals, up and down, and these can be used to mix warm water flows at different temperatures, here 20 degrees Celsius and 70 degrees Celsius. For instance, if up is set to 1, you can see that we'll increase the warm water flow, and this will affect the temperature at the exit of the mixing valve, and the temperature will increase. In this case, we work without position feedback. In that case, well, you have binary outputs that signal when the valve is either entirely closed, fully closed, or fully open. In other situations, well, you work with feedback, and of course you can use this feedback of the valve opening in your control. The solution of this temperature control problem comes in the form of a so-called step controller. Well, the solution is to recycle a PI or PID controller that sets the set point for the opening of this three-way mixing valve. This set point is then compared with the actual valve position, and of course this presupposes that we have here position feedback, and here you have an error, right? And this error is what you have here on this axis, right? If this error is sufficiently large, right, well, you will have a 1 here, and a 1 corresponds to up, right? So the three-way mixing valve will open, right? If the error is sufficiently negative, then you'll have -1, and -1 corresponds to down, that is set to 1, right? So you'll have that the three-way mixing valve will close, and well, if it is sufficiently small to be in this zone over here, well, up will be to 0 and down will be 0, so the position of the valve will be maintained. And as you can see here, using this width, you can make sure that there is a minimum break time, right? And using this hysteresis, you can impose a minimum pulse time. So this is a nonlinearity that is also called a 3-point hysteresis. So this is the implementation of the temperature step controller when you have access to the valve position feedback. If not, what you can do is model the valve position, right? Since we have here an electro valve, well, the model is very simple. It will be an integrating system, an integrator with integrating time constant, the motor time that we have introduced before. So this valve model will take the binary signals up and down and produce an emulated valve position. Of course, the output of the model is not going to be 100% precise, and with time it could be that the output will be off with respect to the actual valve position. But what you can do is use these binary signals that signal when the valve is entirely closed or entirely open, right? Assume, for instance, that at some stage the binary signal valve closed is coming. Well, then you know that the valve is entirely closed, and you can reset the output of the integrator to 0%. Similarly, if the binary signal valve open is set to 1, then you can reset the output of the integrator to 100%. In this subsection, we look at level control, and we will see that in some cases we have to implement a nonlinear PI, also called the E-square PI, that can be implemented using a recycling of the standard PI algorithm. For level control, the actual target or set point value is the volume, but often it is assumed that the diameter or the cross section is constant, so we use the substitute value level. Of course, if this cross section is not constant, and this is for instance the case when the tank is lying on its side, right, or you have a conical tank, then the dynamics become non-linear. We have seen this when we have talked about integrating processes, and indeed the dynamics between the difference between the input and output flows to the level is that of an integrating process, and well, the relation is linear, as I said, if this cross section is constant. Well, typically level control has little influence on production, right? But the level should be kept in a certain band, and this band is application dependent, as we will see later. Depending on the process, either the input or the output flow is regulated. And for this type of process, as for any integrating process, you have to beware of oscillations, and this is especially the case if you have several integrating systems in series, so here several coupled tanks. As I just said, level control can be done on the input or output flow, and different implementations are possible. So control directly on the valve, well, a cascade level to flow, and a cascade level to flow plus feed forward, and this will depend on the available signals, the disturbances, and if feed forward is likely to bring an improvement, yes or no. You will see that the IDs that here are applied to level control can be applied also to other types of integrating systems, and we'll see later in this subsection, well, an analogy with the voltage control of the DC bus of an inverter, which is really a power electronics application. Well, let us have a look at these different control structures. So here we have a storage tank that is controlled by controlling the level using the input flow. So the most simple solution is to use a simple level controller that will directly actuate the valve, right? If you have access to the flow measurement at the input, and if there are, well, load disturbances, then it makes sense to implement a cascade control. Remember that in this case, if you have, well, noise, high frequency noise on the level, you should filter it out, otherwise you'll find it at the output of this, well, primary level controller, and, well, you will ask high frequency variations to this, well, local flow controller, which is not a good thing. If you have also access to the output flow, then you can use it as a feed forward, and this will have a stabilizing effect. And you could do similar things if you have a number of storage tanks in series. Well, in the sequel, we'll consider two cases, two types of problems. The first one is tight level control, and in that case, well, a PI controller is often used. Remember that, well, the integral action should not be too aggressive. Remember this construction of the perfect sign by taking two integrators in series and by closing the loop. If you have an integrating type system with a PI controller with a lot of integral action, well, you have constructed the ideal oscillation, right? So you should use a PI controller, but well, use this integral action with parsimony. The second type of problem is average level or loose level control. The idea is that you allow the level to vary around the set point and that you use the tank as a buffer. And in that case, a non-linear PI controller will be a good solution. Let us illustrate these two types of level control problems. An example of tight level control and another of average level control, and both examples come from the paper industry. If you go back to the introduction of the course, you will remember that the stock, the paper stock, is brought on the wire system and the web is formed. The water is going through the wire to be collected and filtered. This white water, it's called like that because it contains water, of course, and fibers, needs to be filtered, and this is done using this rotating filter. The white water, so this water with fibers, is brought in this rotating drum, and at the exterior of this drum, on the walls of this drum, you have filter cloth. Well, the water is going through the cloth and the fibers get stuck in the filter cloth, right? And they kind of cluster together. Since this is rotating, well, at some stage you have a spray here, and well, the clustered fibers, they are sprayed upon and they fall into, well, the drum, where they float and are removed by flotation. Well, there is a control of the speed of the drum that is based on the pressure difference, well, inside the drum and outside the drum. This is not the control that is interesting for us. We are interested in the level control, and this type of level control is a tight level control because the manufacturer gives you a very specific set point that you should follow, and there should not be fluctuations in the level, because for instance, when the water column becomes too high, well, this weight of this water column will be high and this will damage the filter cloth. The next example is an example of average level control. The stock flow coming from the stock preparation is going through several steps of cyclonic separation. This is to remove the heavy parts. These cyclones operate best when the stock flow through the cyclone is as smooth as possible, so no sudden changes in the stock flow through the cyclone is desired. Now imagine that after this cyclone you have a storage tank, right, with a level controller, and that's, well, you have an output flow of this storage tank, which is of course the stock demand of the machines. What will happen when those machines start is that you'll have a step-like stock demand. Imagine now that you have a very tight level controller, right? If you have the perfect level controller, this step-like flow at the output, well, you'll find it also at the input. Of course, the level control is not perfect, so you'll have a fluctuation of the level, but you still have a very sharp change of the stock flow through the cyclone, which is not desired. So here, clearly in this application, tight level control is not something that you desire. Well, here what you would desire is that you allow, if this is the set point here, temporary variations from the set point. Of course, in the end, slowly PV will return to set point, but these large excursions around the set point will smoothen this step-like stock demand at the output of the storage tank to something that looks like this, and that is not as sharp as what we have seen previously with a tight level control, and this will be acceptable for a good operation of the cyclone. This type of level control is called average level control, buffer tank control, surge tank control. You will find different names in the literature. Well, in this example, that is for your information only, you will see a very similar situation than that of the cyclonic separation with this hydrogen kart, and the algorithm that you'll obtain for average level control can be applied to this situation as well. Well, the analogy will be as follows. The level control is replaced by a DC bus voltage control. The stock flow demand from production will be replaced by a current demand to the DC motors. The level control, using the stock flow coming from the stock preparation and that goes through this cyclonic separation, is now replaced by a DC bus voltage control using the current coming from an hydrogen fuel cell. Again, we have this situation that it is best to operate the hydrogen fuel cell with a current that is as smooth as possible. Here again, we need average level control of the voltage of the DC bus, because when you push the accelerator, you do not want this step-like increase in the current to cause a step-like change in the current coming from the hydrogen fuel cell. So what you like is to have an average level control of the voltage of the DC bus, so to allow excursions of the voltage around the set point, right, to smoothen this current demand so that you do not have sharp variations of the current and that you have an operation of the hydrogen fuel cell that is correct. For tight level control, you'll use a PI controller. Of course, by now you should know that you shouldn't use too much integral action. You might think that a P controller is sufficient because you have an integrator in the process. Well, this is sufficient for set point tracking, but this is not sufficient for disturbance rejection. If you have a presence of a disturbance in the system at the input of the system, this will lead into a steady state error, right? Of course, an I controller is completely out of the picture because you would have two integrators in series and then you close the loop. This is the perfect oscillator. So you'll use, as I said, a PI controller with not too much integral action. As I said before, beware of oscillations, especially if you have several tanks in series. Do not use derivative action, and again, integrating action should be used with caution. Level is typically a noisy signal, so you'll have a kind of spiky behavior. So what you can do is detuning, so tune the controller less aggressively, but of course the preferred solution is to use filtering of the level signal. The next two slides are for your information only. You might think that P action might be sufficient as you have an integrator in the system, but if you go through the calculations and you compute, well, PV as a function of set point, load disturbance and output disturbance, and you look at the steady state behavior, you can do this by using this final value theorem, you can see that PV in steady state, well, is not influenced by output disturbances, so you can reject them. You can follow a change in set point, so it's okay for tracking, but you cannot reject load disturbances. So this is why for level control not a P controller is used but a PI controller. Of course, you shouldn't add too much integral action to prevent oscillations. What we'll do here is derive the IMC PID tuning rules for an integrating process with delay. I said PID tuning, here it will be PI tuning, and you can use it to tune a PI controller for tight level control. So the integrating process with delay is described as follows, and as I've said before, very often what is used is this PID type approximation, where this exponential of minus theta s is approximated by 1 minus theta s, and this is true for small theta, and in this case, well, it's small with respect to the desired closed loop time constant TCLP that we want to impose, right? And as I've said, we are going to use a PI controller. Here it is, right? And what we want to do is, well, impose this closed loop time constant. So what we'll have to do is look at the transfer function from set point to PV. This is a reminder that IMC tuning is, well, made for set point tracking problems, and this closed loop transfer function is this one over here, right? We will see that we'll have at the denominator a second order polynomial. If we want to impose a closed loop time constant TCLP, we will have to impose that both poles are -1 over TCLP, right? So in other words, we'll have to impose that the denominator of this closed loop transfer function is, well, TCLP, or TCLP is the closed loop time constant we want to impose, TCLP s plus 1 squared. And if you do the calculation, this is what you obtain. Well, remember that we have approximated the system by, well, Kp, so this is approximate 1 minus theta s over s, right? And we're using a PI control, so Kc, right? Ti s plus 1 over Ti s. So this one is PC over 1 plus PC. So if you plug this in, this is what you obtain. If you go through the calculations and you put everything under the same denominator, this is what you obtain. So this denominator of the closed loop transfer function is given over here. And you have to equate this to the denominator we had imposed in the previous slide. So this one here is TCLP square, right? And this is 2 times TCLP. This is kind of obvious, right? So this will yield Ti, right? So what we'll do here is write this one over here. So we'll have TCLP squared. We'll bring this one on the other side, plus theta Ti is equal to Ti over Kp Kc, right? So we can isolate Kc. Kc is equal to 1 over Kp. This makes sense. Kc is always, or inversely proportional to the process gain. We'll have Ti over TCLP squared plus theta Ti. So this one here, theta Ti, will be theta squared plus 2 TCLP theta. So if you look here at this one, this is really TCLP plus theta square. So we end up with 1 over Kp. Ti you can replace by this one, theta plus 2 TCLP. And the denominator, as we had said, it's TCLP plus theta square. So TCLP square plus theta square plus the double product. And this is indeed what we see over here. And if you go and look in the IMC tuning table and you look at an integrating system with delay theta, you will see that indeed these are the parameters that you'll find in the table. Well, these are the IMC tuning parameters for an integrating process with delay. And if the delay is 0, well, in this formula you set theta to 0, and this reduces to the following tuning parameters for an integrating process without delay. And you will see that this is a quite easy formula. All you need is the process gain of the integrator. So that type of integrating system is very easy to tune. You only need the process gain and the desired closed loop transfer function. In the case of an integrating process without delay, the exact response using the IMC tuning parameters can be obtained, right? If we go back 2 slides, you can see that the closed loop response is over here. At the denominator, of course, we'll have the denominator that we have imposed, and at the numerator, since theta is equal to 0, we'll have TIS plus 1, and TI will be here 2 times TCLP. So indeed you obtain this transfer function that you can rewrite as follows, given that Ti is 2 times TCLP. And you see here that you have a response that is that of a lead lag system followed by a first order response. Well, if the set point changes in the form of a step, right, well, the response of the lead lag system is given here in green, and I hope this does not come as a surprise. Otherwise, you'll have to go back to the section on process behavior. As you can see at the origin here, well, we have the high frequency gain, which is 2, right? And when t evolves to infinity, so in steady state, well, we have the process gain of this part, which is 1. Well, now you have to imagine this response here in green going through a first order system with time constant TCLP, and you'll have a response of this type. So you can see that, well, I'm C tuning for an integrating system without delay produces this type of response with a slight overshoot of the set point. Note that this might suggest that you can choose TCLP as small as you want, but of course there is also another curve that you should look at, and it's MV, and of course the smaller you choose the desired closed loop time constant, the more aggressive the controller will be. Well, let us now look at average level control. So here the level will not be tightly connected to the set point. It will be allowed to fluctuate around the set point in a band or in bands set by alarm limits, right? So if the disturbance, the error, the control error is small, then you expect, well, a slight control action, and the proportional action will be weak, right? Remember that for level control, well, the action of the controller is mainly proportional action. Well, if you go outside the bands, right, if the control error increases, then you expect a strong control action, so a strong proportional action. And there are essentially two ways to implement this. Well, the first one is to work with a dead band or with dead bands, right? And then we can make the following representation, right? So this is the controller gain that will be adapted, and this is the control error. It can be positive and negative, and this is set point minus PV, right? So what we can do is set a band, for instance here in blue, and if the error is in this band, well, we take a small value of the controller gain, right? Whereas when we are outside, we have here a high controller gain. But this leads to discontinuous control action, and this is not desired, right? Of course, what you could do is kind of have a variation here from one to the other in a particular zone, but this is going to make things difficult. What you could do also is, well, work with several zones. So here we had one zone here in blue. You could do, well, another zone over here, do it in red. And if you're in the red zone, not in the blue zone, then we could use, for instance, a more aggressive controller, and outside this red zone an even more aggressive controller, right? So this could work, this is going to lead to discontinuous control. You could probably do something about it by having small zones that will connect this, but this will not work very well, and you'll have a lot of tuning constants, and this, well, is a form of the gain scheduling that we'll be introducing later on in the course, a form of gain scheduling on the control error. The other approach is much simpler. It's the approach of a nonlinear PI controller. Well, this sounds complicated, but you'll see this is quite easy, and this is also the preferred approach, and it will ask for less tuning constants, in fact only 1 or 2 depending on the case. And the idea is very simple. In order to have a continuous control action, we let the controller gain be proportional to the absolute controller error. So Kc is proportional to the absolute value of the error. So depending on the proportionality factor, what you will have here is that Kc will evolve linearly with the absolute value of the error. Well, the most general form of the nonlinear PI controller that implements this idea that was introduced in the previous slide is this one over here. Well, you recognize a PI controller, but you have here a nonlinearity, right? A nonlinearity that acts on the control error. So here you have one candidate, but you can come up with other nonlinearities. Well, of course, such a nonlinearity has to remain positive for all control errors. So another candidate would be this one with, well, the absolute error replaced by the error squared, right? So in this case, the nonlinearity is an offset plus a gain times the absolute value of the error. What is often done is simplify this most general form by taking A is equal to 0, and then you have two gains, Kc and this K nonlinear, right? So instead of using two gains, you set this one to 1, and you end up with this form here that is often used for average level control. As you can see, in the proportional part we have Kc times the error squared, and this is why this controller is also called an error squared PI controller. Well, you could actually take this algorithm, discretize it and implement it in an FB, but you would have to, well, make sure that you have a faceplate, that you implement all different modes, internal set point, manual tracking mode, and so on. So this would take a lot of work, right? So what you can do is, instead of implementing this algorithm yourself, recycle a PI algorithm as follows. In order to recycle the PI algorithm and obtain a nonlinear PI, what you can do is take the original PID block FB and continuously write on the input that corresponds to the controller gain a value that corresponds to the absolute value of the error times some constant that is now the new design parameter. You can always have access to the error either as an output of the PID block or simply by taking the difference SP minus PV. Well, since you always write a value on Kc, and the absolute value of the error times the new design parameter, well, you will no longer be able to access this parameter for change in the faceplate. In the faceplate, you'll see a gain Kc that will be changing continuously, right? So to interact with the tuning of the nonlinear PI controller, you'll have to make sure that you have access to this parameter in the human machine interface, right? Well, this implementation and the tuning of this recycled nonlinear PI requires training. Well, this gain has to be chosen not too big, and also you have to beware of the integral time constant. So start with integral time constants that are sufficiently high and decrease if necessary. Well, another form of this nonlinear PI can be found in the literature, and what you see over here is that this nonlinearity is only acting on the proportional part, whereas in the previous form this nonlinearity was in front here and was acting on both the proportional and the integral part. Well, this form of the nonlinear PI controller can not be implemented using the recycling of an existing PI controller. To implement this form, you'll have to program this controller yourself in an FB, and it is therefore much less popular. In this subsection, we look at the Smith predictor, a control solution for processes with a large dead time. And here we mean large dead time in comparison with the main time constant. Well, we have seen that when the dead time is large compared to the main time constant of the system, this has a destabilizing effect. Remember the effect on the stability margins. There are two solutions. Either you use a PI controller and you decrease the controller gain. Remember, this is also what is happening when you use IMC tuning. If the delay is increasing with respect to the main time constant, we had seen that, for instance, for a Broida system, first order with delay, well, the gain of the controller was decreasing. The other idea is to use dead time compensation, and this is going to lead to the Smith predictor. The important variable is the so-called controllability ratio, alpha, and this is theta, the delay over the main time constant. Well, in essence, when alpha is small, let us say smaller than 0.1, then the process is easy to control. From 0.5 up to 2, well, it's possible to tune a PID controller, but of course it becomes more and more difficult, and it might lead to a slow, sluggish control. Above alpha is equal to 2, then it's for sure not advisable to use a PID controller, and you should use the Smith predictor that is proposed in this section, or the internal model controller that will be proposed in the next section. Well, we have seen in the section on process behavior that if you have a process with dead time and you use the classical controller, for instance a PI controller or PID controller, well, then if this controller is tuned aggressively, this will produce oscillations on PV if the dead time is large with respect to the main time constant, right? So in this subsection, what we'll do is split the process in dead time, and the rest of the dynamics we'll put it in a block, and we'll call it process dynamics without dead time. So if you have, for instance, a Broida model, a first order model with delay, so this part will go in this block over here, and the first order will go in this part. So if you have a delay in the process, you can always write the process as the delay, and then in a separate block the remaining dynamics without this delay. Well, let us now look at this Smith predictor, and again we start from our process that we have split in two parts, the dead time and the process without the dynamics. The idea of a Smith predictor is very simple. It is to construct a prediction here of PV using the model, but of course the model without the delay. And instead of using PV, we're going to use the predicted PV, and this is a prediction that is in advance of PV, right? And it's in advance of a time that corresponds to the dead time. We're going to use this one for control, right? So the predicted PV is sent to the controller, right? And as you can see, well, we have managed to keep the dead time out of the control loop, and this is why this is called dead time compensation. Well, although this is a very good idea and we have managed to keep out the dead time outside the control loop, this idea has two main shortcomings, right? We work with a model, and as you know, a model is never an exact representation of the system. If we look, for instance, at the static gain, well, the actual static gain will be Kp, but the static gain of the model will probably be different, right? So if we have here a controller with integral action, we'll have that the predicted PV will be on set point in steady state. But since the gains are different here, well, the PV is going to be different from the predicted PV in steady state, so it's not going to be on set point and will have a non-zero steady state error, right? Well, the second problem comes from the disturbances that are present here at the output. Of course, the job of the controller is to reject those disturbances, but in this first version of the Smith predictor, well, the control mechanism is not aware of these disturbances, so it will not be able to reject them. Well, there is a very easy way to notice that there are disturbances acting on the process and that the model is not exact. What we have to do is to compare the process with the overall model. So this is the model without the dead time, followed by the estimated dead time, right? So by taking this difference here, we'll be able to see that there is a disturbance acting, and we'll see, even if there are no disturbances, that we have a problem with the model, okay, that the model is not an exact representation of this actual system. So this error we'll now have to use in our Smith predictor scheme. Well, this is how the model error, and this is the difference between what is measured on the actual system and what is obtained from the model, is integrated in the Smith predictor. Well, this model error is simply added to correct the prediction that is sent to the controller. The idea is as follows. Assume that we have here a set point change. Well, in first instance, this means before the process is reacting because of the delay, only the model is used to control the system. After a time that corresponds to the time delay, of course, the process is starting to react, and what you can do is compare the process with the output of the model, right? And you can use that information to correct. If this error is, for instance, positive, right, this means that PV is larger than the modeled PV. Well, it is added this positive error, right? And what you will see is that the prediction will increase, and what the controller will do is slow down the process by decreasing MV. Well, the fact that the error is positive can have two sources. Well, the first one comes from the model, right? If the actual process gain is higher than the process gain used in the model, well, you'll have a PV that is higher than the predicted PV, right? Another source is that, well, the model could be more or less correct, but that there is a disturbance acting on the process. But whatever the source of the error, if you have here a positive error, a PV that is too large with respect to what is predicted, well, the associated controller scheme, the Smith predictor, is going to slow down the system by decreasing MV. Well, let us now have a look at the steady state situation, right? And in steady state, what we would like is that PV is on set point, and of course what we'll assume is that we have integral action in the controller. Most often this controller will simply be a PI controller. So if we reach a steady state, this means that, well, the closed loop system is stable, and this is of course what we'll assume. If we reach a steady state, since we have integral action, we'll have that the predicted PV is equal to set point in steady state, of course, right? So let us have a look at this part of the control scheme in steady state. We'll have MV. Here we'll have Kp, the actual gain of the system, and here in the model we'll have, well, the estimated process gain, right? So MV is constant, it's going in, and here to emulate the effect of a disturbance, we'll assume here a constant disturbance. We'll call it D simply, and of course what we have over here is PV, right? So if we look at this scheme over here in steady state, what will be happening is something like this. Plus, minus, we'll have a plus over here, and the error, the model error in steady state will be added, and this is therefore the predicted PV, right? And we know that the predicted PV will be on set point. But as you can see here in steady state, we have something that is added over here and it is subtracted over here, right? So we can clearly see that in steady state the predicted PV is equal to PV, right? Since the predicted PV is on set point, but therefore PV is on set point as well. So if there is a steady state, so if the closed loop system is stable, we see that PV will be on set point. In the Smith predictor, this model error of course needs to be between quotes reasonable. So you need a good model of the process, and especially the estimation of theta needs to be accurate, right? Because if this estimation of the delay, the dead time, is not accurate, you could do worse with the Smith predictor than without. Remember that we have seen cases where the dead time is varying, right? If you have a transport delay, well, depending on the speed of the machine, the dead time is going to change. So in the Smith predictor, you have, for instance, in that case, to make sure that the delay changes with the production line speed. What you could do to ensure that you have a good model is run the model in parallel with the process without using it, just for comparison. So before you commission the Smith predictor, to have confidence in this model and to adapt it, and once you're sure that the result is satisfactory, you can use it in your Smith predictor. So running the model in parallel is something that can be done, of course, without any danger. When commissioning a Smith predictor, it is very important to associate this commissioning with operator training, so that the operators know that what we will see on their faceplate of the PI controller is the predicted PV and not the actual PV. They have to understand the difference, right? But they can use this predicted PV because it is an anticipation of what will happen on the actual system. So it is very important to make sure that on the HMI you have a separate window where you see both the actual PV and the predictive PV with, of course, the action of the controller. This is the Smith predictor that we have obtained by gradually adapting the control structure. We have just removed the process. We can now reorganize things to have a block with the set point and PV at the input and MV at the output. Well, let us start the reorganization. Here we haven't changed a thing. We have just organized things to the left. Right here we have PV that is added. So what you can do is put PV here at the outside. This is what you see over here. And instead of adding over here, what you can do is add over here. And in the end, you have, well, the Smith predictor block organized as usually with the controller. You have the set point and PV at the input and MV at the output. But you can see that inside the block we have a controller, usually a PI controller, and it is associated to a model of the process. When implementing a Smith predictor, very often a Broida type model is used, and you can use a step experiment and then approximate the response by that of a first order system with delay, and then you obtain this Broida model Kp 1 over T bar S plus 1 exponential of minus theta bar S. And this is this graphical approximation method that we have seen in the section on process behavior. So when implementing this Smith predictor, what we do is compensate for the delay, right? So for the controller, which is often a PI controller, it is as if the process is this Broida model without the delay. So in this particular case, a first order system. So you can tune the PI controller as if the dead time is not present, right? And if you tune a PI controller using the IMC PID tuning method for a first order system with gain Kp and time constant T bar, this is how you should do it, right? Go and have a look in the IMC tuning table at the first line in case A, and you will see that these are the PI parameters. Of course, it is also possible to use higher order models, right? So if you use a second order model, 2 time constants and a delay, well, then you can tune the PI controller for the Smith predictor as if the process is a second order system. In summary, if the actual system is a lag system, so several first order systems in series, and you have used a step response and the graphical methods to obtain a Broida model, Kp 1 over T bar S plus 1 exponential of minus theta bar S, well, then you can implement the Smith predictor as follows. Here you have a first order system with gain Kp, time constant T bar. The estimated dead time is then T bar, and you can very easily tune the PI controller using the IMC tuning parameters for the first order system, since this Smith predictor is going to, between quotes, take out the delay out of the control loop. Well, in the next few slides we do a few simulations with a Siemens predictor. The process is a Broida model, so first order with delay, and as usual you can split the process in process without delay and the actual delay. Then of course for the model we'll do something similar. We'll have a model of the dynamics without delay and then a model of the delay itself, right? To make the link with the predictive PID that will follow, we'll use the names PV fast, PVF here, as the output of the model without delay, and the output of the overall model will be called PV slow, right, because it goes through the delay. You can see that several signals here have different colors, and that's how you will recognize them in the plots. The predicted PV is constructed from the fast PV plus the error, and in first instance will work with an exact model, right? The PI controller is tuned using the IMC tuning method, and we do as if the process is a first order system, because the Siemens predictor is taking out the delay out of the control loop, right? So this is how you tune the PI controller, and the desired closed loop time constant is 0.25, so a quarter of the time constant in open loop. Let us have a look at the simulations when the model is exact. This means that the model error E will be 0 at all times, as you can see. From the perspective of the controller, well, it is as if a first order system without the delay is controlled at all times. The PI controller is tuned based on the knowledge of the model, and since here we want to accelerate the system, well, this will yield a gain, a controller gain of 4, and this is why when the set point change is done, this error at the time of the change is producing a proportional kick of 40, right? And the actual PV here in green, right, is following the predicted PV, or the fast PV, because the fast PV here in blue lies, well, just behind or below this predicted PV, just as the actual PV in green lies below the red line here. Well, it is following this predictive PV with a delay of 2.5 seconds. Well, what we can now do is look at what happens if the model is not exact. So what we'll do is consider 3 cases. Well, a case where the gain is not exact, and there is a mistake in the gain. Another case where the time constant is not exact, and another case where the dead time is not exact. I will go only in the details of the first case where the gain is not exact, and I will leave you the other 2 as an exercise. Well, let us have a look at what happens if the gain in the model is chosen too small, 0.8 instead of 1. Well, the first impact is of course on the controller gain, right? You can see over here we divide by the gain in the model. Since it's only 0.8, the gain is now going to be 5 instead of 4 before, and this means that we have here a proportional kick of 50, whereas before we had 40. Okay, so we know that for the actual system, right, we need a proportional kick of 40 to have a response with a desired closed loop time constant TCLP, but we have a proportional kick of 50, so the controller is too aggressive. And this is seen after the period of the delay, because you can see that the value of PV is higher than the value of the model. So there is a positive error, and this positive error is added on the fast PV, right? We see now a difference between the fast PV and the predicted PV. And since this predicted PV is going to increase, right, but the controller is reacting by slowing down the system. And as we had anticipated, well, both the predicted PV and the actual PV are going to go to set point, and we have a zero steady state error. Well, if you see such a response, you can immediately see that there is something wrong with the gain of the model, right? If you have a steady state error, as you clearly can see over here, this is a sign that there is something wrong with the static gain in the model. Well, on the web page associated to the course, you'll find this Simulink file that will allow you to simulate a Smith predictor on a process and understand the mechanism that is behind this Smith predictor. As you can see, the process has been initialized to the process used in the slides, and here we have the Smith predictor. If you click on the faceplate, well, of course you'll have to introduce the model parameters, and for the tuning of the PI controller you'll have to, well, use this parameter gamma to set the desired closed loop time constant as a function of the open loop time constant. Well, we can also look under the mask and have a look at the implementation of the Smith predictor. Here you recognize the PI controller that will generate the MV, and this MV is sent to the process, and what is collected back is the process. So here in between you have to imagine the process. As is usual with a Smith predictor, what is done is that the model without delay is used for feedback, right? And added on this fast PV, well, you have the model error, and the model error is PV minus, well, what comes out of the overall model, and this is the model with delay, and what comes out here is the slow PV, right? This implementation is a bit different than the implementation in the slides, but it will look like the implementation of the predictive PID controller, and we'll see that the Smith predictor is a particular case of this predictive PID controller. Well, if we run the model, we obtain the curves of the slides, and for instance what we can do now is consider a case where, for instance, the delay is chosen, well, wrong, and well, the mistake is large, and we'll have a look at what happens. So you can see that we still have a stable system, but as you can see, if you make a mistake in the delay of the model, this can have more severe consequences than errors on the time constant or the gain of the system. So if you implement a Smith predictor, well, you'll have to pay a lot of attention at the estimation of the delay. But again, here, if you look at the curves, it's kind of obvious from, well, the output of the overall model here in red and the actual PV that you have made a mistake in the delay. So by observing the curves, you can correct the parameter estimation. Well, this Smith predictor can easily be programmed in PCS7 once you have the blocks. So here you have the PID controller, and here you have the actual, well, Smith predictor, right? So I will show you the important blocks. So here you have the model without delay, and this is going to be added here in this adder block to the model error, right? And the model error, this is what is coming from PV minus what is coming out of the overall model, and the overall model is the dynamics without delay going then through the delay, right? And this predicted PV is going to the PV of the controller. So we can have a look at the interface in, well, WinCC, and this is how you should make it, right? So that you see that it is not a normal controller, right? And you should give access to all the signals. So the actual PV, the fast PV, the slow PV, the model error, and in the faceplate you'll see the predicted PV. So in this case the actual process is a second order system with delay, right? And in the Smith predictor we have used a first order system with delay, so we have neglected this secondary time constant. What you can do is have a look at a set point change, right? And we'll go up to 90 degrees and see what is happening. Well, this is the steady state response, and as you can see here, the actual PV, this line over here, is, well, going to set point, so the static error is 0. In the beginning of the response, so before the delay, there is no difference between the predicted PV and the PV that is coming out of the fast model. And here at some stage, well, after the delay, well, the model reacts as a first order system. Okay, this is normal, and the process reacts as a second order system. So here the slope initially is 0, right? So we have a model error. Since the model is faster, right, the error is negative, and this explains here what you see over here, right? So there is a decrease in the predicted PV, and this leads to a small boost of MV. In any case, well, PV goes to set point and you have a response that is non-oscillating. If you would use a PI controller on a process like this one, where the dead time is in the neighborhood of 2 times the main time constant, well, you would have difficulties in tuning the PI controller. It's time for a little quiz, and without a surprise, it's about the Smith predictor and it's about tuning, right? So a Smith predictor is implemented to control the Broida system that is given over here, and you can see here that the ratio delay to time constant is larger than 2, so it would be difficult to, if not impossible, to tune a PI controller for that. So we use a Smith predictor, right? And of course we have to tune the underlying controller, and we ask you to use the IMC tuning method to tune the Smith predictor PID controller that is given over here. As you can see, it is working on SP minus the predicted PV, and for information here, TFD is fixed here and it's TD over 10, and the idea is to achieve a closed loop time constant of 5 seconds. So here are the 5 alternatives, right? And over here, well, you have the IMC PID tuning table. So as usual, use the pause button, the rewind button, and the forward button to try to find the answer by yourself. Well, remember that when you're tuning the PID controller associated to a Smith predictor, you have to do as if the delay is not present, because the, well, Smith predictor will take out the delay from the control loop. So the process that we are tuning is not this one, but the associated process without delay, and in this case it's a first order system with gain Kp is equal to 2 and a time constant of 5. So we have to look here at the first row in the IMC tuning table, right? And we have a look here, and we know that the closed loop, the desired closed loop time constant is 5 seconds, and also the open loop time constant is 5 seconds. So this ratio over here is 1, but Kc is this ratio divided by the gain of the process. The gain of the process is 2, so the gain of the controller is a half, right? And the integral time constant is the time constant of the process, so in this case 5. So the correct answer is C, gain of the controller a half and integral time constant 5 seconds. And of course, since the process is first order, we have removed the delay from the loop using this Smith predictor. Well, for a first order system you do not need derivative action.